Hello, AP Stat students. Today we will do 7.2 notes. So in 7.1, we talked about parameters and statistics, and we mentioned bias and variability. In this chapter, we will talk about sample proportions and sample means. When we're talking about categorical data, we are interested in proportions. So how good is the statistic p hat as an estimate of the parameter p? The sampling distribution of p hat answers this question. So this scenario right here is from an applet, and you can Google and go to Rosman Chance, and there's a lot of cool applets that simulate these processes. So it's a good one to go around and play with. So consider the approximate sampling distributions generated by a simulation in which simple random samples of Reese's Pieces are drawn from a population whose proportion of orange candies is 0.45. So in this candy machine, the true population proportion of the orange candies is 0.45. What this situation is showing on the left is you're taking a sample size of 25 candies and you're going to run 400 samples. And then you're going to get a statistic from each sample, and then you're going to plot the statistic, and that gives you that sampling distribution, which is right here. Okay. So if you look, this first one, the picture that you see of the orange candies, yellow and the brown, that statistic is 0.48 is orange, just for that particular one. And of course, then it's plotted on the sampling distribution. So 400 of these are run of sample size 25, and you end up getting a mean of 0.448 and a standard deviation of 0.103 of that sampling distribution. On the right, the sample size has been increased to 50 candies at a time, and these are all done randomly, and the number of samples is still 400. The population proportion is 0.45 for both of them. And for this particular one, notice the mean of the sampling distribution is 0.451, which is almost spot on to the true population proportion, and the standard deviation has decreased, which brings us back to what we talked about in 7.1. We said that when we increase the sample size, that decreases the spread, so it makes the standard deviation smaller. And if you look at the shapes also, this one's pretty symmetrical looking, but you still have numbers far to the right and to the left. Whereas on the right, this ends up being, you could almost really, oh, wow, I didn't draw it very good job, but it's more normal looking. It's more of that bell-shaped curve that we desire. And when something is normal, you can use the Normalcdf to calculate probabilities. And that's the goal of statistics. What are the chances? That's what we want to answer. So when something is normal, you can use the Normalcdf and calculate probabilities. So what did we notice about the shape, center, and spread of each sampling distribution? For the shape, in some cases, the sampling distribution of p hat can be approximated by a normal curve. This seems to depend on both the sample size n, so n is your sample size, and the proportion of the population, and that would be p. The mean of the distribution, so that's the proper notation on the left. So make sure you know your notation. So this is the mean of the sampling distribution is equal to the population proportion. This makes sense because the sample proportion p hat is an unbiased estimator of p. For a specific value of p, the standard deviation, so this is the standard deviation of the sampling distribution, it gets smaller as n gets larger. The value of the value of the standard deviation of the sampling distribution depends on both n and p. Okay, now we're getting to our first formulas for the semester. So this formula is these two formulas are in section 3 of your formula sheet on the back page of the very front page. And that is the mean of a sampling distribution is equal to the population proportion. That's the first formula. The second formula, and we need those. We need the mean and standard deviation to calculate probabilities, but that's not all we need. We need to make sure that it's approximately normal so we can actually calculate a probability. The standard deviation of the sampling distribution of p hat is, so the standard deviation of the sampling distribution is equal to the population proportion times 1 minus p divided by the sample size, and you take the square root of it. And so for our Reese's Pieces, we can actually put in numbers here. We would do 0.45 was our population proportion. 1 minus 0.45 is 0.55 times, and this is for the first one, so the sample size being 25. If you did the second one, then you would just put 50 in the denominator, and everything else is going to be the same. So you can only use that formula for the standard deviation of the sampling distribution as long as the independence condition is satisfied. You cannot use it if the 10% condition is not met. And when I say the 10%, okay, that's what we need to put over here. So the population, N is the population, its size has to be greater than or equal to 10 times the sample size. And as long as that is satisfied, because when we're doing sampling, when we're dealing especially with people, we're not going to replace them back. So since the independence condition is not going to be met that way, you want to make sure that the 10% rule is satisfied. And so that has to hold true. As n increases, the sampling distribution of p hat becomes approximately normal. Before you perform the calculation, you must check that the normal condition is satisfied. And for when we check the normal condition, you actually have to show your work, and you don't just say, oh, it's satisfied. So here are the two conditions that will satisfy the normal condition. So the sample size times the population proportion has to be greater than or equal to 10, and the sample size times 1 minus p has to be greater than or equal to 10. If those two are met, and that's called the large counts condition, then you can say that it's approximately normal. We learned that at the end of first semester, really towards the end. And now we are going to do some problems based on this information. So these are the important formulas you need. So you need this one, and you can only use that formula as long as the 10% rule is satisfied, and then these two. That's not really a formula, it's a condition. So let's go ahead and do an example. About 75% of young adult internet users ages 18 to 29 watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion P in the sample who watch online videos. So the simple random sample of 1,000, that's our N, it's our sample size. And this would be P. About 75% of young adult internet users watch online videos. What is the mean of the sampling distribution of P hat? So let's do the notation correctly. So the mean of the sampling distribution is equal to the population proportion. And I circled the population proportion is 75%, so we'll just write that as a decimal. So the mean of our sampling distribution is equal to 0.75. It's going to be the same as the population proportion P. Okay. Find the standard deviation of the sampling distribution of P hat. check that the 10% condition is met. So we should always check that the 10% condition is met before we actually use the formula. So what is the proper way of writing this? You can write it in a phrase, you can write it in a sentence form. So we are doing sampling without replacement. So we are going to have to use the population has to be greater than or equal to 10 times the sample size. So the sample size is 1,000. Multiply that by 10. Is it reasonable to assume that there are greater than or equal to 10,000 young adult internet users? It's totally reasonable. So for the 10% condition, it is reasonable to assume that there are greater than or equal to 10,000 young adult internet users. Now, do you need to show that you multiplied 10 times 1,000? Not for this one. It's only when you're doing the normal condition. That one, you can easily multiply 10 times any number. You don't have to show any work there. So we know it's reasonable. Therefore, the 10% condition is met. Now we can use the standard deviation formula. So the standard deviation of the sampling distribution is equal to the square root of p times 1 minus p. So p is 0.75. Therefore, 1 minus p will be 0.25 over our sample size, which is 1,000. So multiply the stuff in the numerator, divide by 1,000, take the square root of it, and you are going to get 0.01369. And that is our standard deviation of the sampling distribution. C. Is the sampling distribution of p hat approximately normal? Check that the normal condition is met. So here's where we want to show our work. So do you have to write the formula? It's never going to hurt, but you don't have to. You can just do both of it and show both of them. So n is 1,000 times p is 0.75. Is that greater than or equal to 10? And you don't just say yes. You actually have to show the ending values. So multiply 1,000 times 0.75, so you get 750. That is greater than or equal to 10. I just show a check mark. That's met, but you have to show the other one. So n times 1 minus p is greater than or equal to 10. The more you do this, and you'll realize you'll be doing it like often and often, it's just becomes so automatic. So we have 1,000 times 1 minus p, which is 0.25. Is that greater than or equal to 10? So this is 250. It is indeed greater than or equal to 10. So yes, the normal condition has been met. So the sampling distribution of p hat is approximately normal. Never say exactly normal. So. And now that we know that it's normal, we could do probability calculations. This particular problem is not asking us, but the last one will. If the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? So the mean would be the same because it's going to be unaffected, but the standard deviation would become smaller. And you can always plug in numbers to figure that out. If you were to replace 9,000 the denominator instead of 1,000, you would get a smaller standard deviation. So you can always do that. The mean would be the same. But the standard deviation would become smaller. And now for our last problem, and this is a 4-step problem, which our textbook is really big on. And honestly, the 4-step problem is just a way to organize your free response answers. And your textbook will tell you that use the 4-step process to answer this question, but on an AP exam, it's not going to tell you. You just want to be able to make sure you follow these 4 steps so that you answer the actual question. So let's take a look at this. And for this particular problem, I've laid out most of it for you. On your test, I would just give you the opening paragraph and you have to come up with everything. So here's the problem. A polling organization asks an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. So that is P. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? So 35% is our population proportion, and within 2 percentage points would be 2 percentage points below and 2 percentage points above. So 33 to 37%. So and that usually that last statement, the last question is going to be what you're stating. So you're in your state portion. So the 4-step is state, plan, do, and conclude. In the state portion, just state what you're being asked to find. So we want to find the probability that the sample proportion falls between that 0.33 and 0.37. We want to know the probability of that sample, what it's going to be. So for our plan portion, before we do all the do part is the calculations. The plan portion, you want to make sure the 10% condition has been satisfied and that the normal condition has been met. So we have a simple random sample of size n equals 1,500 drawn from a population in which the proportion is p equals 0.35 that attends college within 50 miles from home. The independence condition is met because it is reasonable to assume that there are more than 15,000 first-year college students. So just take the 1,500 and multiply by 10. The normal condition has been met because if you look at the second sentence, the distribution is approximately normal because n times p, so 1,500 times 0.35 is equal to 525, which is greater than or equal to 10. So check. And then n times 1 minus p, so 1,500 times 0.65, that equals 975, and that's greater than or equal to 10. So once you know that you can use the standard deviation formula and you know that it's approximately normal, you can calculate a probability. So in our do portion, we need to figure out the mean and the standard deviation. So the mean of our sampling distribution is equal to the mean of the population proportion, so 0.35. So we need that in our normal CDF. And now we can do our standard deviation since we met our 10% condition. So the standard deviation of the sampling distribution is equal to the square root of p times 1 minus p, so that would be 0.65, divided by the sample size, which is 1,500, take the square root of it. And honestly, when you're rounding, I would try and keep as many decimal places as you can so you minimize errors, and we'll talk about errors later on in the semester. So I didn't for the previous problem because I knew that I didn't have to calculate any kind of probability. So this is 0.012315302. So we have the two things that we needed, the mean and standard deviation. So now we want to find the probability that the sampling distribution statistic is between 33 and 37%. So greater than or equal to 0.33, sorry, and less than or equal to 0.37. And we can use our normal CDF. Kind of looks terrible. And hopefully you guys remember what to use here. And I if you forgot, I'm going to walk you through it, so don't be alarmed. You have 4 numbers here. Go into parentheses. The first one is your lower bound, and our lower bound is left, so it is 0.33. Label these values. You don't just put random numbers in here. Label it lower bound. And I never know how you will get docked points if you don't label things. And honestly, I think you guys who are going to take the AP exam will have another open notes exam like last year's students did. And last year's students only missed a quarter. So I'm pretty positive, but I'm not going to say for sure. Our upper bound is 0.37. If you guys were in class, you can just yell out all these things. So, our mean is 0.35. Label it. And you don't have to put like mean of the sampling distribution. You could just put mean, just put mu, and you're okay with that. And our standard deviation is 0.2123153.021. The key thing is, how do we get to the normal CDF? So if you forgot, the normal CDF is part of our distribution menu. And to get to that, you go to second and you go to VARs on your graphing calculator. And then you select the one that says normal CDF. And of course, if you have a newer calculator, it's going to tell you what number should you put in for the lower bound. It gives you the names, or the phrases lower bound, upper bound, mean, standard deviation. But if you don't have that, you have an older calculator, you have to just memorize the order. So just remember LB, UB, mean, and standard deviation. And so you enter that into your calculator and hit calculate. 0.8956 is our probability. So in our conclusion, so state and conclusions kind of just go together because you're answering what you're stating in the beginning. So I don't know, probably shouldn't have an arrow going that way, but about 89.56% of all simple random samples of size 1500 will give a result within 2 percentage points of the truth about the population. Or you could have said something like about 89.5%, 56% of all simple random samples of size 1500 will give a result between 0.33 and 0.37. And those are your notes for today. Have a great day, AP Stat students. Sorry.